Alright, so today I want to figure out what is the magnetic field at the origin of this wire configuration. Now I've driven some axes where this is the y-axis and this is the x-axis. Besides that, the shape is as follows. We have a semicircle and then kind of half a square, because if I continued at this side it would be a perfect square. So in order to find the magnetic field, we're going to have to use the Biot-Savart law. It states E is equal to mu naught over 4 pi integral of dl cross what I will call the displacement vector, and I will explain what each piece is, divided by script r squared. Now, you have to integrate this piece over the entire wire. Specifically, dl, I did forget a, apologies, IDL for units, but dl essentially is the vector that goes around with the current. Script r, or this fancy r, is a vector that points from the wire to wherever I'm interested. So for the semicircle, it would point from here to here. And for each individual point, say something here, would point like that. Now this is made up of a lot of complicated pieces, so let's break this up into this piece of the wire and that piece of the wire. Breaking it up like this is perfectly valid because the magnetic fields add just like normal vectors do. So let's tackle the circle first. In the circle, and I will call that the integral over c for circle. The integral over the circle, I have to find each of these components. So BC is equal to mu naught I over 4 pi. My dl has to be the length vector, and it has to follow the current. Now the current is going counterclockwise, so it's essentially starting from the bottom of my circle and then moving forward. So my dl is going to be a, because that's the length of this semicircle, d phi, because it integrates over phi, and then minus phi hat. It's just phi hat, and I'll explain why after. Now I have the cross product of the vector that points from the wire, specifically to the origin, which in this case is going to be minus r hat. Now I have to divide by the magnitude of the length below, but that's just really the same, so it's just a squared. Now solving this integral isn't too bad. Mu naught I over 4 pi integral. Well, phi cross r. Phi is a vector pointing in this direction, and r is a vector pointing inward. So if I do the right-hand rule, I get a vector pointing into the board. So this is going to be a minus z hat, which is good since you wanted to find bz at the origin. And then r cross phi just gives us nothing but the z hat vector. And then we're left with a d phi divided by a squared, and our integration bounds start from this part of the circle going this way. So 3 pi over 2 pi over 2. And if I evaluate this integral, this is going to give me, oh my God, this should not be a minus. pi over 2 minus 3 pi over 2, which is just mu naught I 4 pi a c hat times minus pi. Alright, so now we found the magnetic field for the circle at the center, and I know this pi is probably making you all go crazy, but there is a reason for that. Now I want to find the magnetic field of the square root. So again, it's a square root, it's like a double square. So, we have to do a little bit of intuition before we really start. Let's consider breaking this up into smaller wires. So this piece is the same thing as this piece plus that piece plus that piece plus that piece, and then we return that one. Now, which direction was the current flowing in all these cases? Well, it was going counterclockwise, so it must follow the same schematic. And now before we even start, we actually can cancel out a lot of things. We want the magnetic field specifically in the z direction. And if you look at the integral for dl, we know it follows the path of the current. So let's inspect, I will call this one gamma 1, and this one 2, 3, 4, 5, gamma 5. So, the integral over gamma 1 for the line integral is going to be equal to mu naught 4 pi integral. So dl in this case for gamma 1 is pointing up, so the differential element for that is y dy, and I have to cross it with the distance from the current to the origin. However, that distance is strictly a y value, so it's going to be cross some y hat. And I don't even need to continue, because we know a vector crossed with itself gives us 0. So this integral is already going to go to 0. Now, I can do the exact same argument for gamma 5, because now the dl element is still positive dy in the y-hat direction, and since the displacement is also in the same direction, they cancel out again, you get a 0. So these two give a net 0 contribution. The integral for these two, which I will label accordingly as gamma 2, gamma 4, will also have a very interesting consequence. Let me set up the integral for those specifically. So for gamma 2, this is going to be mu naught I over 4 pi times the integral. So for gamma 2, we're essentially starting from 0 all the way to negative b. So that's the first bound. And my integrating dl is minus dx, but it's in the x hat direction. And then I have to do the cross product with the distance vector. So we need to find the distance vector from the origin to this component, which we've used this now. I'll draw out a small little schematic. So if this distance right here is told to us is also b, then the displacement from here to here, or any point arbitrarily, which is a distance x away, can be done using a triangle, where this will be some arbitrary theta. But we can actually talk about the vector as, let's see, it has to point from the wire to the origin. So first we would go down b, times y and a negative, so that brings us down to here. And now we need to go to the right, plus x hat. But remember, this must be a unit vector, so we have to overall divide by its magnitude. However, we know that the magnitude of this by Pythagoras is just b squared plus x squared, square root of 1/2. But we also have an r squared over there, which is the exact same length. The exponents add, and my integral becomes the following.